Okay, in this video, we are going to cover review problems for day 2 of the Math 136 final exam, and we're going to look at questions 10 through 19. So this is the second half of our review here. Starting off with number 10, this one says, how much money should be invested today in order to have $10,000 in 20 years if the rate is 4.5% compounded monthly? Okay, we have two different formulas that we've used for interest. So the key words here are compounded monthly. That tells us which formula to use. And the one we need for compounded monthly looks like this. Just as an aside, the other interest formula is this one. And that's the one we use for interest compounded continuously. Continuously is this one. Anything else other than continuously is going to be the one we have written here. So let's identify the information given us in the problem. How much money should be invested today in order to have $10,000 in 20 years? So this 10,000 is not our beginning balance. That's how much we're going to end up with. So that's going to be our A for this problem. In 20 years, so 20 is our time, that'll be T. The rate is 4.5%. So our interest rate, remember when we do calculations, we always want to change that to a decimal. There's our interest rate. And then we also need to figure out what N is. N is the number of compounding periods in a year. Since this one is compounded monthly, there are 12 months in a year, so our N is going to be 12. And that means the question was, how much should we invest today? We don't know our beginning balance. P is what we're going to be solving for. So we plug everything into our equation here. The 10,000 goes in for A. P is our variable. R divided by 12, which is N, and then N times T. Okay, there's our equation that we need to solve. Now notice what we have over here. We have P, which we're solving for, times this entire expression. P times that expression means that in order to solve this equation, we can really kind of do it in one step. We just divide. I know it's kind of big and kind of messy, but we can divide by that whole thing. If you like, 12 times 20, we could just go ahead and multiply that out. That is 240. So we divide both sides by that same thing. And you can see that this then is going to be the calculation we need over here. They cancel, and we are left with P equals this expression that I outlined in orange. So we need to grab our calculator to type that in. Okay, if you have the multi-view calculator, you can use the fraction button and type that all in at once. Put your 10,000 on the top. And then go down to your denominator. We need our parentheses. We'll do 1 plus 0.045 divided by 12. You could have used your fraction button again there, but just to make it look a little simpler, I just did it as a division rather than as a fraction. And we want to raise that whole denominator to the 240 power. So there's what it would look like on your multi-view calculator. If you don't have the multi-view, you can still do it in one step. You just might need another set of parentheses. And there's our answer. So our calculator spits out 4,072.54612. Okay, that's not the answer we want to give when we're talking about money. If there are no rounding directions in the problem, if we're talking about money, we want to round to 2 decimal places because that would be showing dollars and cents. So if we want to round to 2 decimal places, we look what comes next and we see, yes, we do need to round up. So there's our final answer, our starting amount if we want to end up with $10,000 in 20 years. Okay, next one, number 11. We're getting into a natural exponential function here. Then they are asking us to graph this. It will be helpful if we know a little bit about a basic exponential function before we try to graph this one. So this function they've given here goes with a parent function of e to the x. And a few things we know about any exponential function, and it applies to this one with e as the base. The domain of an exponential function, that means what am I allowed to plug in for x, is all real numbers. The range of an exponential function, however, is not all real numbers. It's only positive values that we get for y. And any parent exponential function has an asymptote at y equals 0. It has a horizontal asymptote, okay? So real quick, I'm just going to sketch in what that parent function looks like. It's got that asymptote here. It's going to have an intercept at 1. It's going to look something like that, okay? That's just for background information. That's not what we're graphing here. So what we want to do is we want to graph what I highlighted in yellow here, and you can see compared to this parent function that we're discussing, this has a couple transformations going on. That x plus 3 up in the exponent, that is going to be a shift 3 units to the left. And then that plus 1 that's out separate, that's not in the exponent, that's going to be a shift 1 unit up. Okay, so if we take these things and kind of apply those transformations, that asymptote of our original function that used to be at y equals 0, when we shift a horizontal line to the left, that doesn't change anything because it's horizontal. But when we shift it up by 1, that does change things. So our new asymptote is going to be right here. Okay, because it got shifted up 1. And then our domain and range, we can use those, or if you're not comfortable with them, you don't really have to think about those too much. What's going to be helpful here is to think about what x values to plug in. When we do sort of a general or parent exponential function, a lot of times I go from -2 to +2 on my x values. That's not going to be as helpful here because this graph has been shifted 3 units to the left. So instead of starting at -2, which is usually my favorite number to start with exponentials, I'm going to take that -2 and shift it 3 units to the left. So I'm going to start with -5. So those are the x values that I'm going to pick. Again, this is, you can plug those in on your calculator. This is another case where you could use that table button to make yourself a t-table. Press table, and we'll clear out the function we had in there before. This time we're going to use our exponential, so second and natural log gives us that e to the x plus 3, and then use our arrow to get out of the exponent to do the plus 1. Okay, so there's our function. We hit enter, and this time I'm going to go ahead and let the calculator go ahead and make the t-table for me. I'm going to change it to auto. Okay, so I'm having trouble getting my arrow over there if you can't tell. Up. And then it's because there's a lag and I'm being impatient. There we go. Auto is now flashing. So I hit enter. And then I go down and I hit enter. And you can see now it kind of made a t-table for me already. It started at 0. I want to back up and look at some negative numbers, but I can just use my arrow to go back as far as I want. So here, what I picked was -5, so I can read off the table. When I plug in -5, that is 1.1. It's got a lot of decimals there, but when we're graphing, really 1 decimal place is sufficient. For -4, we get a 1.36. I'm going to round that to 1.4. Use my arrow to go down a couple more. When x equals -3, we get a +2. When x equals -2, we get a 3.7. And when x equals -1, we get an 8.4. So I can go ahead and take all those points and plot them on my graph. -5 and 1.1. So that's pretty close to 1. It's going to be not touching that asymptote, but we're getting close. -4 and 1.4. Just do your best to estimate with these decimals. -3 and 2. -2 and 3.7. And -1 and 8.4. Okay, so we get a nice little exponential curve there. Sorry, my drawing abilities aren't great on the computer screen, but you get the idea. There's our exponential function that has been shifted to the left by 3 and up by 1. Number 12 says you have $5,000 to place in a CD for 5 years. A CD is a special savings account. A CD pays 3.6% annual interest compounded continuously. How much will the CD be worth at the end of 5 years? So here's our magic words: compounded continuously. That tells us which interest formula to use. Since it's compounded continuously, we want to use our natural exponential function, this one, and identify what we know. We have $5,000 to place in a CD, so that's going to be our starting value. So that's P. We're starting with $5,000 for 5 years. So there's our time. 3.6% interest means our R will be 0.036. Change it to a decimal. How much will it be worth at the end of 5 years? That means we are solving for A. We don't know our ending amount. So we plug in everything we know. Oops, not P. I want to actually plug in the number. R is 0.036 times T, which is 5. I'll go ahead and show you that on the calculator real quick since we have it here. Clearing out from our last one. Okay, so 5,000 times E. To get E, we need the shift and then the natural log button, and then E to the 0.036 times 5. There's our exponent. Again, if you don't have a multi-view, you may need parentheses around that exponent when you type it into your calculator. And we get 5,986.086816. Again, there are no rounding directions. So since it's money, we want to go to 2 decimal places. So the answer we want to report is $5,986.09. That's how much we would end up with in our savings account. Okay, next up, we're going to start looking at some logarithms. We're given a logarithmic function here, and we are asked to find the domain, the range, and the asymptote. So let's start with domain. When we learned about logarithms, one thing we learned is that you cannot take the logarithm of 0, and you cannot take the logarithm of a negative number. So that means whatever is in the argument of your logarithm has to be greater than 0. So the way we find the domain is we take whatever's in the log, whatever the argument is, set that greater than 0, not greater than or equal to, strictly greater than. So then it's pretty easy to see that our domain would be that x has to be greater than -5. This one doesn't specify, but if we wanted to put that into interval notation, it would be -5 to +infinity. There's our domain. The range for a logarithmic function, you just got to remember, is pretty easy. Think about the graph. The range is all real numbers. And then our asymptote. The asymptote is going to be dealing with the argument again. Take the argument of that logarithm and set it equal to 0. So the asymptote and the domain will be related to each other. So the asymptote happens at x equals -5. That's the value that our graph is going to get closer and closer to, but it can't actually ever reach that value. That's our asymptote. Number 14, we now have a logarithmic equation. This type of logarithmic equation, you'll notice there are some terms that have logs and some terms that do not. Anytime you have an equation like that, the first thing you want to do is move your terms around so that all your logs are on one side and anything that's not a log is on the other side. So the first thing I'm going to do is subtract this log of x minus 2 from both sides of the equation. What I get then, I can't combine these terms just yet. I'm going to do that in my next step, but I'm just going to write it out. Okay, just moved that log to the left. After you have all your logs on the same side, you want to use your properties of logarithms to combine those two. Anytime we have two logs of the same base that are subtracted, we can combine them into a single log using division. Okay, so combine your logs. And then your next step, now that we have a single log and a constant, we want to use the definition of logarithm to rewrite this into exponential form. So first thing we need to remember is that when we just have the word log with no little number down here, no subscript, that is the common log, and that is a subscript of 10. We just don't usually write the 10. So when we go to rewrite this in its exponential form, 10 will be our base. The answer to the logarithm is always your exponent, and we set that equal to our argument. Okay, so 10 squared, that's 100. We can go ahead and multiply that out. We want to solve this, get rid of that denominator, multiply both sides by x minus 2. So I'm going to distribute, remember 10 squared is 100. I'm going to distribute that 100, so I get 100x minus 200 equals, and over here we had some canceling going on, so it equals x plus 3. I am going to subtract the x to bring it over here. I'm also going to add the 200 to take that one over to the right. So we end up with 100x minus x is 99x on the left side, and 3 plus 200 is 203 on the right side. So our final step, divide both sides, and we get x is 203 divided by 99. Seems like a good answer, but anytime your original equation had logarithms in them, you need to check your answer to make sure this is within the domain of your log. So what we're looking for is we want to know, is the argument of each logarithm, does it stay positive when I plug this in, when I plug this value in for x? So 203 over 99 plus 3, when I plug it into this first set of parentheses, that's definitely a positive number because I'm adding two positive numbers together. That one works out okay. I need to check the second set of parentheses also, 203 over 99 minus 2. If you're not sure, plug it into your calculator. Do you get a positive number or not? It turns out you do. You will get a positive number. So this answer checks out just fine with our logs, and that is our solution. Okay, number 15 is similar. Again, we have an equation that has some logarithms and some constants. So remember what I said in the last problem, we want to make sure all the logs are on the same side. They already are, so that's good. Next up, when the logs are all on one side, we want to use our properties of logs to combine them. This time we have a plus in between the two logs with a matching base. So if we have a plus in the middle, we combine using multiplication. Combine your logs, then rewrite into exponential form using the definition of logarithm. So the little number, the subscript, that is your base. The answer from the logarithm becomes your exponent, and you set that equal to your logarithm argument. It's using the definition. 3 cubed is 27. And we'll need to go ahead and FOIL multiply this out. So we get x squared. We'll get a minus 2x and a plus 4x and minus 8. We now have a quadratic equation. Remember, we have several methods for solving quadratics. Make sure you use a quadratic method. Don't go crazy here. So I want one side of my equation to be 0. And then I'm going to try to factor the other side. This one looks like it should turn out pretty good. X squared is x times x. Factors of 35 that are going to give me a positive 2. That would be 5 and 7 with a minus on the 5 and a plus on the 7. So I set each one of those factors equal to 0. If x minus 5 is 0, I get x equals 5. And if x plus 7 is 0, I get -7. So two potential solutions. Be careful. Always go back and check them in every log that was in your original problem. If I take 5 and I put it in for x, I get 5 plus 4, which is 9. That's a positive number. That's good to go. If I take 5 and put it in here, x minus 2, 5 minus 2 is positive 3. That's still good. That one is a good solution. -7, if I take it and plug it in up here, I get -7 plus 4, which is -3. You can't take the log of -3, so that is an extraneous solution. That one does not work. We just have our single answer, x equals 5. Okay, next up, number 16. Solve the equation, and we have a nice little exponential equation there. They want us to write our answer as an exact answer and round it to 2 decimal places. So we'll be giving our answer in 2 forms. Okay, in order to solve an exponential equation, the first thing you want to do is you want to isolate the piece of the equation that has your variable exponent. So the first thing I'm going to do here is divide both sides of that equation by 4 so that on the left those two cancel and I'm just left with 5 raised to the 2x. On the right, I simplify and I get 6. Once the exponential part is by itself, is isolated, then we have to get that variable out of the exponent. Right now it's stuck in the exponent. We need to get it out. And that's where we're going to use logarithms. We're going to take the log of both sides of this equation. We do that because then by one of our properties of logarithms, we can take this exponent and move it out front to be a coefficient. Okay, we have x multiplied by 2 and multiplied by log 5. So in one step, I can just divide by both of those numbers to move them to the other side. Remember log 5? It's just a number. It's some kind of long, crazy decimal, but it is just a number. So on the left, the 2 and the log 5 cancel. I'm left behind with just x equals. So here is our exact answer. It's always going to be the symbolic answer that is your exact answer right there. That's one of our solutions. We also want an answer rounded to 2 decimal places, so that's when we'd have to grab our calculator. And to type that in, you can use your fraction button or you can use your division. Okay, I'll go ahead and do this one with division since not everybody has a fraction button. So I'm going to use a lot of parentheses just to make sure it does things right. So parentheses, log 6, close, close. There's my numerator. Divided by, I'm going to do more parentheses, 2 times log 5. Again, close, close, because I did an extra set of parentheses, plus we've got the argument of the logarithm. Our calculator is going to spit out 0.556641376. It asked us rounded to 2 decimals. So we check out the second decimal place. Look what comes next. We do need to round up. So the answer we report is 0.56. Okay, next up, we have a similar situation again. We have exponentials and we have our variable is stuck up there in the exponent. So we're going to use a similar method to solve this one. We're going to use logarithms and their properties to get those variables out of the exponent. So step 1 on number 17 is we are going to take the log of both sides. We do that because then through the properties of logarithms, we can move those exponents out front. Be careful here on the right because this exponent, when we move it out front, we need to put parentheses around it, okay, because it's the whole thing times log 5. So I'm not going to do anything on the left right now. And on the right, I'm going to distribute this log 5 because remember, I'm trying to solve for x. I can't solve for x if it's trapped inside the parentheses. So I'm going to distribute that log 5 to get rid of those parentheses. 1 times log 5 is just log 5. Okay, keep in mind our goal, we're trying to solve for x. If we want to solve for x, that means any term with an x in it has to be on the same side of the equation. So I'm going to subtract this term to move it over so it can join the other term that has an x in it. Okay, we're trying to solve for x. X is now in 2 separate terms. In order to solve for it, we're going to factor it out front, so it's just occurring in one place. So factor that x out front. And now we have x times this big old log expression. So to solve for x, we're going to divide by that big old log expression. So we'll divide both sides by the whole thing that's in parentheses. On the left, again, we get some canceling, which is what we planned for. That's how we did it on purpose. And on the right, that is our answer right there. This one did not ask for a rounded answer. So we would just give this exact answer. You can do some things with the properties of logarithms to simplify this even further, but it's sufficient for you just to leave it like that. Okay, number 18. Tamika deposited $5,000 at 9% interest, it should say interest, compounded continuously. Find the time required for the amount to double using continuous compounding. Approximate to 2 decimal places. So again, we're talking about interest. We have 2 choices for our formula, but since this one is compounded continuously, we want to use the one with the natural exponential in it. Okay, what do we know? We know she's going to start with $5,000. That's her deposit amount or her beginning balance. We know the interest rate is 9%. Find the time. So time is what we're going to be solving for. We don't know that yet. The time for the amount to double. So the amount she ends with, her ending balance, it didn't tell us the exact value in the problem, but it told us how to figure out what the value should be. She's going to start with $5,000. We wanted to know how long it takes for that amount to double. So the ending amount would be 5,000 times 2, which is 10,000. So let's plug all this in. Okay, and we are solving for t. We wanted to know how long it's going to take. This is kind of like when we did 2 examples ago. Our variable is up there in the exponent. So I'm going to start by getting rid of that coefficient. I always like to use 2 colors. Hold on. Divide both sides by 5,000. 10,000 divided by 5,000 is 2. And over here, the 5,000s cancel. Okay, last time we did this, I took the log of both sides. I just used the common log. This time, it's going to simplify things a little bit if we take the natural log of both sides. You can do either or. We could get the right answer either way. But since we have this natural exponential function, I'm going to take the natural log of both sides of the equation. Again, because of the properties of logarithms, we can pull this exponent out front and turn it into a coefficient. And what we have going on right here, the natural log of e, if you were to type this into your calculator, you'd have to do the natural log of e, and you'd have to put a 1 in for the exponent. That e always needs a number after it. But what you will find out is that the natural log of e is 1, because natural log and e are inverses of each other. So this really just is gone. That is equal to 1. Oh, I forgot my 9 in there. Hold on, back up. When I was copying it down, did you notice that? Sorry about that. 0.09 t times the natural log of e. So that's gone because that's just equal to 1. So now we can just divide both sides by 0.09. So we get T equals, here it does ask us to approximate to 2 decimal places. So that's a hint that you want to grab your calculator. This time I'll use the fraction button. You can do it either way. Up top, we have the natural log of 2. Close the parentheses. Then down arrow for the denominator, we have 0.09. We hit enter, and our calculator spits out 7.70163, blah, 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 more numbers. What we need to do is round to 2 decimal places. So we look at our second decimal place, and since a 1 comes after it, we're just going to report 7.70 years. Now that's an acceptable answer. There are some instructors, some textbooks that would want you to put a little bit more critical thinking into this and think if it asked, find the amount of time required for the money to double. So if I really don't round here, if I call this 7.70, technically it's going to take a little bit more than 7.70 years for it to double because it's not a decimal that just ends at 0. It's 7.70163, etc. So I think some people would say that the more appropriate answer would be 7.71 because it will not quite have doubled yet by 7.70. But we would accept either answer for that one, unless your instructor tells you differently. Okay, last question on the review sheet. Here we go. Number 19 says, a drug is eliminated from the body through urine. Suppose that for an initial dose of 75 milligrams, the amount, A of t, in the body, t hours later, is given by, and they give us a nice little exponential function there. What is the half-life of the drug? Approximate to 2 decimal places. So they gave us this function. And we have to know a little here, what does it mean by the half-life of the drug? The half-life is the amount of time it takes for you to have half of what you started with, okay? So in this case, if we started with a dose of 75 milligrams, 75 divided by 2 is 37.5. That's going to be our ending amount. So we plug that in on the other side of the equation. And we are solving for t, the length of time. We want to know how much time it takes for us to get to that half amount that we started with. So this one solved is very much like the last one. We'll divide both sides by 75. And we get over here 0.5 equals, over here the 75's cancel, and we have 0.8 raised to the power of t. Here you can take the natural log or the common log of both sides. It doesn't matter which one. I'll just go ahead and use natural log again because that's what we used on the last example. You're going to see we don't get quite as nice canceling going on because we didn't have a natural exponential function to start with. Okay, we took the log of both sides, or in this case, the natural log of both sides, because then by the properties of logarithms, we can take this exponent and move it out front to a coefficient. We have t times the natural log of 0.8, so we'll divide both sides by the natural log of 0.8. So t is equal to natural log of 0.5 over natural log of 0.8, which you can grab your calculator, type that in. You'll get 3.10628 and some more digits. But again, let's look at our directions. Approximate to 2 decimal places. So we would want to report 3.11, and it was t in hours. So it takes 3.11 hours is the half-life of this medication that we're studying. And that's it for this one. Good luck on your exam.